Okay, folks. Thank you all for coming on to the SRG seminar. We have one speaker. Needs no real introduction, so I'll let him do all of that himself. But please welcome Professor Silvio De Angelis, who's going to talk to us about the inaudible sound of volcanoes.
Yep. Hello, everyone. Thanks for coming. Guess you don't need. I mean, I've been around for quite a long time, so most of you know me. Guess what describes me best is I like mountains that eject stuff into the air. I like mountains in general. I spent most of my life working in earthquake and volcano observatories, and more recently, about 12 years ago, I came to Liverpool, where I became a lecturer, and I'm still here. So I keep doing my research on volcanoes, and along with teaching and all the things we all know. Yeah. Okay. So there's a few slides. This is just to frame the problem of the impact of volcanoes, the hazard related to volcanic activity, and how we deal with it. So one thing that often is not considered is that the impact and hazards of volcanoes are on different time and space scales, with I guess, a general rule of thumb that the shorter term are the local impacts and the longer term are the more global impacts. So you'll see things that range from the immediate consequences of eruptions, so things like lava flows, pyroclastic flows, atmospheric ash, and you will see some other effects like disruption to supply chains if an ash eruption lasts for a long time. Some cases you might have tsunamis where we're looking at island volcanoes, for example. And there's even examples of climate effects of volcanic eruption. A notable example is the Hunga eruption, the most recent one, for which atmospheric warming has been observed in the last few years. Obviously, it's a temporary effect, is not permanent, but they do have the ability of affecting even climate if they're large enough. When we think about hazards, volcanoes, we normally think in terms of primary and secondary hazards. Primary hazards are things like ash, lava flows, pyroclastic flows, primary lahars, so mud flows generated by the melting of an ice cap on a glaciated volcano. And then secondary hazards, so these are secondary lahars, so these are the ones that are linked to climate, so triggered by rain, tsunamis, and even epidemic disease, famine in the most extreme cases, even though these are, I would guess, a little bit more in the past now. So some critical factors that control how volcanic activity impacts people, infrastructure, society. Listed there, they're pretty obvious. Population exposure, development, style of activity is an important one, and volcano monitoring and early warning. So how capable is a given country, a given volcano observatory to handle volcanic arrest and eruption. This is a map that shows Human Development Index. So these essentially, the colors are proxies for how developed countries are. There's different things that go into this, GDP, education, a number of things. I'm assuming everyone is an earth scientist or environmental scientist or supposedly linked to some of these disciplines. So you will have an idea where volcanoes are distributed on the globe, and you will see that there's a bit of a correlation between some countries with a fairly low Human Development Index and volcanoes. Surprisingly, or perhaps not to me, however, the countries that are more affected are not the ones at the lowest end of this scale, but they're one that normally are included in the low to middle income in the ODA list of countries. So they're countries that have slightly more developed than the very bottom of the scale. It's two factors. There's some resources to invest, even though they're still in the ODA list. And the other factor is the style of activity that happen to be in places where the style of activity is not as threatening, and also the population density is not as large, and the population is not as close to volcanoes. A typical example would be the Eastern African Rift, as opposed to Central America. So there's different things that need to be considered. How do we deal with this? Obviously, there's planning, but in the short term, which is what we mostly do at Liverpool, it's about early warning. It's about developing the ability of forecasting eruption and communicate this to population. So this is a quote from the UN Secretary General a couple of years ago, pointing out how early warnings are going to be more and more important, especially as we face a climate crisis in the coming years. So the view of early warning has changed a little bit over the last 10 years. It's a lot more people-centered than it used to be. Early warning, most people, like if you asked 15 years ago what they thought early warning was, probably they would answer, well, it's the ability of telling people to get out of the way as soon as possible when something happens. You can probably boil it down to that, but to get to that point, there's a few components that need to be considered. And everyone pretty much acknowledges that there's four main pillars to early warning. One is the ability to detect, observe activity, monitor it, forecast. Then there's the general disaster risk knowledge and management. It has to do with planning. So you can use this knowledge to develop plans, to develop hazard maps, and become aware how you can relocate your population, or you can locate it in the first place. Then there's the ability to disseminate and communicate this knowledge. It's not the same everywhere. If you have to make population aware in the United Kingdom, it's very different than if you have to make population aware, for example, in a small village in Guatemala. And then once you reach out to the people that need to be reached out, you have to develop an ability to respond. So preparedness is important. You need to tell them that there's possible risk, make aware them of the magnitude of the risk, and also tell them how to behave should that happen. So here, we're just dealing with the monitoring part. We're not going into the other three pillars, even though at Liverpool, in the volcanology group, we do engage with other aspects of volcano early warning and early warning in general. So volcanoes are fairly complex systems. So you can see this is a fairly simplistic view, first order view of what a volcano is like. Magma chamber, mostly sort of like semi-spherical, and a conduit that goes up to the surface, somewhat cylindrical. We all know these days that this is not what things are like in reality, but it's a good simplification for first order discussion. There's different places in the volcanic system. All of these places, there's a variety of processes and physical properties involved, and all of these generate signals of different types, and we can measure all of these signals and try to infer what's going on under the surface. So you'll see on the left-hand side a list of sort of things that happen and relevant sort of events. And on the right-hand side of this figure, the relevant techniques that we use to measure these properties and this phenomenon. So for the purpose of this talk, we will be in this region. So we will be at the sort of surface, atmosphere, boundary, and in the atmosphere. Volcanoes are really important systems because if you think about that, they link the subsurface with the atmosphere through a boundary layer. So they sort of like span large part of our planet. Monitoring, you're familiar probably with these techniques. Seismology remains the backbone of most monitoring programs. And if you have limited resources, very likely you're going to buy a seismometer with them if you're monitoring a volcano these days. Fortunately, advances in technology have made access to satellite remote sensing a lot easier. These data are a lot more available. Often they already come in the form of products, so you don't need heavy computational resources to access them and use them for monitoring purposes. So things like the formation maps from satellite InSat data are quite accessible even to countries that might not necessarily have the same resources as others, right? Infrasound has become pretty popular, which is what we will discuss in the next few slides. We're talking about acoustic waves. It's become popular because it's very effective and it can be very low cost. So most volcano monitoring programs these days do have acoustic sensors, and they use them for monitoring detection of activity and early warning. So in specific, the type of activity that I will be discussing is what we refer to as paroxysmal activity. So this just means that a paroxysm is usually defined as the rapid transition from a fusive to explosive regime within time scale of maybe a few hours or few days. And generally it's short-lived. Typical durations are between a few hours to maybe a day. And they are associated with ejection of volcanic ash in the atmosphere and ash plumes, and sometimes pyroclastic density currents, so pyroclastic flows. These are two examples from Mount Etna. I should say, for the purpose of the recording, that where you don't see specific credits, they are my pictures or my graphics, and otherwise you'll see the appropriate credits in the slides. I won't discuss this in detail because I've covered this in a separate talk in the past. But I thought this was a good example of what paroxysmal activity looks like at the sort of extreme end. This is a recording that our team from Liverpool took on in June 2018 when Fuego erupted in Guatemala. This was taken from a vantage point right opposite to the active vent. So you see what paroxysmal activity looks like at the summit. And this is a video that was taken by a friend of mine that lives there from their home of a pyroclastic flow coming towards their house, triggered by that paroxysm. On the left-hand side is a satellite picture of the region, the area where that video of the pyroclastic flow was taken from. So if you just look at the top, doesn't look terribly dramatic. Probably if you look at it at night time, you'll be like, oh, that's a nice display. But then if you look at some of the things that can be generated by that, looks quite different. For context, this pyroclastic flow was generated by a sector collapse. Was not a collapse of the ash column. There was not a collapse of an ash flow. It was just a collapse of the sector of the actual volcanic edifice itself. And this is what the same area looked like after the event. This event lasted maybe about 5 to 6 hours overall from start to end. There were more than 400 people dead and 12,000 people displaced. And I guess it's still the repercussions of this event are still being felt to this day.
Which was your friend's house?
It's safe. We're having instruments installed there, quite close though, 100 meters from the edge of the flow. So the main scientific question that we wanted to ask ourselves in the last 5, 6 years in Liverpool was, can we use acoustic waves? And how can we use them to improve eruption monitoring and early warning? This is just a quick slide with a list of all the partner, or some of them actually, probably missing somebody, partner organizations that have worked with us, and a list of some of the people that I could remember that have worked in our team over the last 5, 6 years and have contributed to that. Most of these people have two things in common. They like volcanoes like I do, and they probably think the science should benefit society. That's how I would summarize that research group. So down to what infrasound is. They're acoustic waves, generally below 20 hertz, so humans cannot hear them. It's acoustic waves, but it's not sound as we're used to. They generated when the atmosphere is perturbed. So as soon as a source of any kind is able to displace the atmosphere, you generate acoustic waves, and these propagate. And we can record them at surprisingly large distances. There are examples of infrasound for volcanic eruptions recorded at thousands of kilometers, up to 10,000 kilometers. So infrasound propagation, for a number of reasons, is very efficient. So it's a very good tool to use. We will deal with local distance recording in this talk. So we are within 10, 15 kilometers, but we have also worked in Liverpool on longer scale, longer distance recording. Because acoustic waves are generated by things that can move the atmosphere, there's a lot of possible sources, not just volcanoes. So sometimes people are surprised to learn that all of these things can actually generate acoustic waves, and some of them will not be able to hear, others will. There are some issues with it, mostly that, especially at local scale. The acoustic wavefield propagates over topography, so it does interact with it. It's affected by wind and by temperature. But however, we can actually account for that. We have numerical tools that allows us to understand how these happens and sort of like make allowances for it. What do they look like? Essentially, they look like a seismogram for those that are familiar with seismograms. It's a time series of excess pressure. So it's a measurement of pressure relative to background, and the background is the atmospheric pressure. So they are a perturbation of the background atmospheric pressure that we experience every day. They're very small. So ambient pressure at sea level is about 100,000 Pascal. A typical very loud noise or infrasound recorded by a volcano is about 100 Pascal at about a few kilometers from the source. So it's a very small fraction of the pressure that you experience every day in your life. So we need very high quality sensitive microphones to record that. And we also need ideal conditions, which fortunately we have. We've developed that knowledge. Why people start using microphones? They have some advantages over seismology. These waveforms that you see on the left-hand side, it's the same event, it's an explosion. The top one is a pressure record, so it's an infrasound record, and the bottom one is a seismic record of the same explosion. So if I showed you them separately, you would probably guess from the top one that it was an explosion or some sort of impulsive event. If I show you just the bottom one, probably you'd say, oh, it's an earthquake. I mean, that's what I would say, not just because one is not an expert. So what's the advantage? The propagation path is simpler. The atmosphere is better behaved than the solid earth in terms of elastic wave propagation. There's less anisotropy, the properties are overall more homogeneous, so the waveforms are simpler. The other thing is that this means that we can easily separate the source from the path in the waveform. So it allows us to understand better the magnitude of an event and of its source. Something that is both an advantage and a limitation is that a microphone can only detect sources that are coupled with the atmosphere. So that's an advantage because essentially allows you to discriminate explosions from other things. It's a disadvantage because what you can detect unrest that is not directly coupled with the atmosphere. So sometimes it's a win, sometimes it's not a win. Some disadvantages, we say, can only get surface sources, or at least those that are shallow enough to displace the atmosphere. The wind affects velocity, even though this is predominantly at long range and very short range, it's generally not a big effect unless the wind field is really strong. There might be, because of refraction from topography, this is very relevant at short range and for steep topographies. We can model this effect. So this is an example of a model that we did back in 2012, so a few years ago. And it's a model of how sound propagates from this volcano in Alaska, Cleveland, all the way to these instruments 650 kilometers away in mainland Alaska. So we can forecast exactly the amplitude of the acoustic waves that we would have recorded there and how long it would take for them to get there. These are particularly favorable conditions. All these red that you see here means that in the top 15 kilometers of the atmosphere, there's very strong winds in Alaska. They're very constant, always blowing in the same direction, and they help the sound to be transported very efficiently. So there's very little attenuation, and this thing can travel like thousands of kilometers because the wind helps it, and it doesn't oppose its propagation. So what do they look like? Some examples. These are all examples of discrete explosions. Common thing amongst all these different examples is that they're short duration, and they have fairly short duration ash plumes associated with them. If you have a more trained eye, you can probably actually, by looking at the shape of the waveforms and the amplitude, guess what type of event has generated those. So they do have a very characteristic individual personality to them. I think most of my colleagues would be able to tell you where they are from and what sort of explosion has generated them. This is what the infrasound looks like when you have a sustained eruption with sort of like an ash plume that goes on for hours and days. It looks fairly different, but if you zoom in, you will soon realize that normally these sort of like very long extended signal are just a sequence of individual explosions coming really fast out one after the other. So if you're more of a mathematical mind, when they get very, very close to one another, you can think of them as a basic wavelet convolved with a sequence of spikes, or Dirac comb, as we like to call it. So there are some, the underlying process, it is still the same. It's just the rate at which the process is occurring that changes and shapes the signal. From now on, I will deal with linear acoustics. So this means that we're dealing with small density pressure fields and only the subsonic range. This is not a limitation. We can do nonlinear acoustics as well. We use linear acoustics because it's the most appropriate for the largest number of eruptions. We can deal with shock waves. There are models for that, but the largest majority of the case studies that we have studied at Liverpool, for them, this is the appropriate framework. So it's entirely possible to do other things. So we've said acoustic waves are generated by fluctuations in fluid flow. And this theory still stands from the 1950s, demonstrated that as you perturb fluid flow inside the flow, there's a number of acoustic sources, the distributed acoustic sources that are generated, and they can be represented in terms of three main mathematical equivalents: monopoles, dipoles, and quadrupoles. Monopoles essentially are linked to acceleration of atmospheric mass. So this tells you, this gives you information of how much stuff is coming out of the volcano as a function of time. Dipoles are pressure fluctuations at solid boundaries, so they're changes in momentum of the flow. So they don't add any mass into the flow, but just change the momentum of the flow. A typical example would be if you have a volcanic vent and the flow hits a topography boundary like a crater wall. That will disturb the momentum of the flow and introduce something that can be represented as a mathematical dipole. Quadrupole is linked to turbulence. It really generally is relevant only for very energetic eruptions that approach the sort of like Mach 1, so that they're sort of approaching the supersonic regime. The last two are grayed out because we discovered at the end of all these efforts that you don't need them. There's way to use the monopole with some tricks, and we'll go through that. So I'll just, this is just one of the two equations that are in this slide set. So this is just a summary of what I said in the previous slide. So P in this equation is your pressure wavefield. So this is what you record with the microphone. It's a time series of pressure perturbations. And we're writing it as the summation of three terms. First one is the monopole. which is a convolution between the monopole Green's function and the mass source term. So that's the time history of our mass or volume is released over time at the source. And then there's a dipole term, which is simply equivalent to two monopoles with opposite phase, one next to the other. And then there's a quadruple term. We will discard this for now, except for a brief mention of the dipole. So if we look at this, what is a Green's function? A Green's function, essentially, you can think about it in simple terms. If you have an impulse at the source, and this impulse travels the atmosphere in this example of acoustic waves, it is the waveform that you would record at your receiver after it has interacted with the atmosphere, with topography, with temperature field, with everything. So it represents the effect of the atmosphere on your reducer. If you are in an ideal world where the atmosphere is homogeneous and isotropic and is bounded by a horizontal surface, which obviously not true, this is your Green's function. So what this means is that your source will be just scaled as the inverse of the distance from the station to the source. So nothing, in that case, nothing else happens to your waveform. This is an example of synthetics in this homogeneous isotropic. So these are examples of two plausible time histories for volume release from a volcanic vent. And this is the waveform. These are the waveforms that you would observe in both cases at different distances, 1 kilometer, 2 kilometers. So you see the same waveform shape, and the only difference between different distances is that the amplitude has decreased as the inverse of the distance. This is the equation that tells us everything. So one, I think people should focus on is that this is a relationship between delta P, which is the signal you record, and the volume flow rate. So how much volume is coming out of the vent as a function of time. So this gives us a simple equation. If you have a recorded time series, you can get the volume flow rate of the eruption from a simple integral. So it's a quite powerful tool. Why is it important? Well, because this is one of the main parameters, if not the main parameters, that go into models of ash plume rise and ash dispersal in the atmosphere, which are used for operational purposes. So it's a key thing to know. The other parameter that's really important is the greatest plume height that the plume can achieve before it starts spreading horizontally. So we'll see how we can use this information starting from the pressure time series and get that one as well. How was it done until now? Using zero-dimensional or empirical models. So these are just a set of equations of that general forms. These are two specific examples, calibrating against the database of measurements. So people collected measurements of eruption rate and plume heights. They put them on a plot, and these are two examples of the best fit law of that shape to that data set. There's some limitations, obviously, because doesn't account for style of activity. The measurements can be inconsistent because they're not all being collected with the same methodology. Most measurements will be from field measurements, so eruptive products divided by an estimate of the duration of the eruption, for example. It doesn't take into account whether it's a weak plume or a strong plume, so whether the wind field is able to bend the plume or not, so that, because one of these axes is the height of the plume, that has an effect. They work reasonably well, that said. So they are still in use at the UK Meteorological Office, which is responsible for ash warnings in that part of the world. But we wanted to improve, we wanted to use data, we wanted to calibrate this relationship, we wanted to be able to do it in real time, most importantly, which is something that you can't do if you require field measurements of volume eruption rates. So some people started quite recently, actually. This is an example from 2014 at Sakurajima volcano in Guatemala, in Japan, excuse me. And they just simply measured the pressure at one station, and they solved that equation to get the volume flow rate out of it. and calculate the time history of volume flow rate at the source, would be this plot. There's several simplifications and assumptions, so that's still an equation that relying on the what we call geometrical spreading, so the amplitude decreases as the inverse of the distance, and there's no other effect accounted into it. There's no vent morphology or edifice topography considered into correcting these pressures. There's no effect of wind considered, and no reflections at the conduit atmosphere interface, which might happen because we have different media, different temperatures, different pressures at that interface. So in Liverpool, we got excited about this and we started writing projects. And we went to Guatemala a few years ago, and we put a bunch of microphones around Fuego. And we said, well, we're just going to apply that. We're just going to build an early warning system based on that. Turns out that it wasn't that easy. So we applied that, and now we see that we have different stations, and those are the time histories of volume flow rate for an explosion. And for different stations, they look quite different. So they don't have the same shape for a thing, which would be okay, fair enough, who cares? But most importantly, they have very different amplitudes, and these have been corrected for the distance between the microphones and the source. So supposedly, minus side effects and noise and different characteristics of microphones, they should roughly look the same. They look quite different. So, but there was a mismatch. So people say, well, let's use inversion instead of just using one single station. So this might mitigate an arbitrary choice of a station. We're not just choosing one, we're using all of them, and we're integrating the information into an inversion. So we decided to try inversion considering a source, monopole, and dipole. And we don't consider the vertical component of the dipole because that would require having measurements above the vent. So it's quite difficult to install a microphone in the atmosphere, even though we recently done it on a balloon. So results are coming soon. And we solved this very simple inversion problem. And what you get is a time history of the volume flow rate. So this one. And then you also get this dipole strength. So this essentially, the job of this dipole strength is to collapse all of those other effects that you didn't consider in the simple theory with just geometrical attenuation. It collapses the event, all the effects of diffractions from topography, wind, temperature. You just plug it in there and just assume that it's represented by that. But we have numerical tools. We can solve equations. So we can actually account for topography. So we started doing that. We built numerical models of how the acoustic wavefield propagates and interacts with topography. And now we're able to account for that. So we can produce simulations like this that show the true propagation of the acoustic wavefield. So you notice, if you look at it carefully, that it doesn't spread the same way in all directions, and you will notice in the vertical cross sections that at times you have diffractions, like here, for example. So we can calculate our Green's functions now based on numerical modeling, and we have removed at least the problem of topography and temperature and wind. We can include all of this. So we went back and did the same inversion using numerical Green's functions instead of using the analytical solutions. And we got very good fit, but there's still a little bit of a dipole there. So it didn't completely disappear. It got much smaller, but it's still there. So the guess at this point was, okay, maybe this represents the directivity of the source because it's the only thing we haven't considered. So we did the same at Etna in Italy, similar results. So we started thinking, okay, it's very computationally intensive, so not really suitable for real time. The monopole is much easier. The dipole, after all, is very small. So do we really care for it? Or is there another way we can account for it? So we came up 2 years ago with this corrected monopole that accounts for all these things. So it's a very simple correction. These corrections all come from numerical modeling, of course, but we have this term, alpha. This term accounts for the directivity of the source. So it tells you how accurate is a monopole representation of your source and whether you need to correct that or not. It's generally something, it's a number between 0.8 and 0.95, generally speaking. That takes care of directivity of the source. This number called infrasound loss, it's attenuation, mostly from topography. You can make maps of attenuation from numerical models. I'll show you one in the next slide. And finally, this R is the reflectivity at the vent. So this is a really important term, because this tells us that the largest amount of energy at the interface between the conduit and the atmosphere is actually reflected back into the conduit. So this is why in the past I didn't mention it, because I'm ashamed now. We're getting extremely large values of volume flow rate, which were not really realistic. After it introduces this correction, now the values are match other measurements that we obtain with radar, for example. So the benchmark with other independent measurements. So we can make these maps of attenuation. This is an example of Etna. The blue colors are places where the sound is strongly attenuated, and the red colors are places where there might be even some constructive interference. So the sound is greater than what you would have expected based on the distance. For those of you that are good at reading pretty low quality maps, you will see that the red is all at the edges of a valley. So there's sort of a steep-sided wall where the sound can sort of reflect and sort of do constructive interference. And because we position the source here in what is called the new southeast crater, these are the summit craters of Etna, which are higher elevation. So the sound is blocked by that topographical barrier. That's why there's that sort of deep blue. The two maps are from two different models. This is from finite difference. It's a numerical model. And this map is just using a simple Fresnel approximation. So it's one-on-one physics. And it's just calculated the attenuation over the diffracted path rather than the direct. So it takes into account barriers to the propagation of the sound. So we went there for 2 years. This is the last project I had, recently published. And we deployed clusters of microphones, so we should call array, which are able to detect activity automatically in real time. And we used that formula to get time series of volume flow rate. In this case, I converted them to jet velocity just through the area, a cross-sectional area of the vent, because we had other benchmarking measurements which were velocity rather than flow rate. And we get this time series, and we can plug these numbers into a plume rise model that we developed recently in collaboration with colleagues at Bristol. And we get an estimate of the maximum plume height during an eruption. This can be real time. It takes less than half a second to do this. And surprisingly, for the two events that we published, they match really well the actual satellite data and other measurements. Obviously, you might argue, well, it's only 2 examples, so you got lucky. We're now going back through a database of about 10 years, and this is consistently observed. So it seems to work well. So it's been translated into an operational tool where these ash dispersal scenarios are generated. So there are models of these that are generated for a range of plume heights and volume flow rates. So that there, every day the system generates them. As soon as the array detects the activity, calculates the volume rate and the plume height, and these are used to select the most appropriate scenario from a library of pre-computed scenarios. And this is now hopefully in the process of being finalized within the next few months and used as an operational tool. So just the last 2 slides briefly, I mentioned eruption early warning. Obviously, what we discussed so far was more like monitoring as an event happens, but can we do something about getting a warning before something, just in the hours, days before something happens? So because we deployed these arrays for having automatic detections of activity, we got a little bit more information out of them. So that arrays for, I won't go into the details, but there are clusters of microphones, maybe 6, 7 microphones crossing space. There's like, you know, within an area of about 100 by 100 meters. And they can tell you when there's activity coming from a specific direction as a function of time. So you get two types of information out of this. You get a detection of activity and how strong the activity is, and you also get how frequently that activity is happening. Turns out that if you combine these two simple metrics into one, it becomes a very powerful parameter for early warning. So if you multiply the amplitude of your pressure within a detection window by the number of detections, in this case per minute, you can build this infrasound parameter, which you see here, plotted in two examples. And this shows a nice exponential increase up to the time of the paroxysm. The time of the paroxysm in these two plots is at the peak of the IP number. So we went back 10 or 12 years, and we redid this calculation for 12 years of data, and it's always the same trend. So it turns out that if you can now calibrate the amplitude by attenuation, so go back and build maps of attenuation in the past, you can calibrate an early warning system. So you can establish thresholds for the levels of activity that correspond to what most people would probably define as a yellow, orange, red, or some sort of traffic light system appropriate. So that's these are the two most important outcomes of this chunk of research over 6-7 years. We were able to estimate eruption source parameters, namely plume height and volume flow rate from infrasound data, and this can be done in real time. And then we are working towards building this early warning system. It's now being tested in Italy, Mexico, some volcanoes in the US, and it's already being used in Guatemala, which formed the basis of an impact case study that I submitted in 2021 for RED, for those of you that are more academically minded. I think it's a good example of how something that started as a pure fundamental science and trying to understand processes that generate an acoustic wavefield turned into an operational tool and into an impact case study. So what's next for me? I got tired of explosions. So I turned to mass flows and some links between debris flow, floods, and climate. So I just recently got awarded 2 projects, one by UKRI and one by NGP, to investigate. I mean, it says debris flows in the heart, but it's a little bit wider scope. It's got landslides, essentially everything that moves gravity-driven at the surface of the Earth, using seismology, infrasound, and deformation data. And I guess, again, the main deliverable will be an early warning system. So in the case of lahars for volcano, we plan to produce real-time inundation maps. So you can be sitting in front of a computer and get within 5-10 minutes a map of where the flow is going to reach. As most grants, we already have built the product. So you see this, it's already installed there, but obviously we haven't revealed that, and we need to refine it. Thank you. Oh, this is our test site, and if you look very carefully, there's rock dollar on this bridge here.
Very much. Anyone have any questions for Silvio?
Something really something simple but fundamental. So you have the attenuation, which is 1/r.
Yes.
Why is it 1/r, not 1/r squared? I'm used to kind of energy spreading out. It goes like 1/r squared.
That's the amplitude, it's not the energy.
So
there's energy would be 1/r squared.
Okay, fine. Okay.
And it's like seismic amplitude versus.
Okay, so it's just what's and the other really silly question is, given your list of applications, have you detected any fictional superheroes?
We detect meteorites,
Sure,
Northern Lights in Alaska.
I can understand that, but extraterrestrials or fictional superheroes, have you?
Depends who you ask. Depends who you ask to. It turns out that if you post your detections as unknown sources on a website in a country that had recent elections, you might find comments. I'm not joking. You actually do find comments like that. So I don't know. Maybe there's hope.
When you were showing the long eruptions with the very densely packed seismic, the equivalent of seismic bands, when you stretch those apart, can you get an idea of this? Is it like a kind of pulsing frequency of those eruptions, or can you tell anything more about eruption behavior by looking at the really tight packed patterns?
It depends. So there's there's a volcanologist are more a better answer in this question, but there's a regime that's called transitional between discrete pulses and what is a sustained flow in the conduit. So you see that transition in the data. This is where these kinds of break down a little bit. You still need to be using individual detections for individual explosive events. So when you go to something that you might think is an extreme case of plume eruption, these might not necessarily work, and you would have to use a different framework, which we have, but it's very, I mean, this is a lot easier to apply and translate into an operational tool.
Is there a technology limitation to it in terms of the sensitivity of the microphones?
No, the microphones will, as long as you install them in appropriate place, which is normally heavily vegetated areas, if you can, or you protect them with noise reducing systems, they work quite well. They can detect our microphones, which we developed in Liverpool. They cost about 200 quid and they detect up to 0.01 Pascal. So tested on the grass in front of the Nicholson, so not the ideal low noise situation.
I'm sorry, I'm having my opening thing as well.
Shout. Okay, so the pulsating behaviour you see in these style of eruptions, have you been able to link that to the deposit characteristics? Because then you can use the deposit characteristics from these recorded eruptions, where we have the infrasound and we know the eruption dynamics, to then interpret more prehistoric eruptions and think about how they've been produced. Is there any attempt to link it to the physical world?
It's part of the grant, and unfortunately I didn't get funded. But I think it can be part. But yes, you're correct. You can do that. I mean, it's something I didn't touch in this presentation, but obviously there's a lot of information that comes from complementary fields. This is something that you can look at rapidly in front of the screen when you're sitting in the room, but you want to understand what generates that. This is essentially just describing the source of the acoustic wavefield. It's not describing anything that has to do with what happens and leads to that. That requires volcanology and physical volcanology, I would say, as well.
But it provides a way to interpret prehistoric eruptions by having.
Yeah, you can match what you saw in the past with what you see today, of course.
Anyone else have any questions for me, Dave?
So a couple of slides ago, you showed that parameter that you were using to help prediction.
Yeah.
So I was just wondering, like, can you see similar things from seismological data, which would tell you the same thing? And does this give you any additional information to that, or is it just the fact that infrasound networks are cheaper to install than seismometers?
That's one component. I mean, it's actually £250 versus £7 grand. So obviously it's a big difference, but you're right, you can see this in the seismic data. The other interesting things, there's a limitation in the interesting aspects about the seismic data. This is a multi-vent system. So in the seismic data, we can actually locate multiple sources at the same time. When one vent is having the paroxysms, the other vent at the summit are still actively gassing, and we can actually see them. But obviously, if you did this trick without separating them, you would end up with an overlap between detections from a vent that is not actually the one that's producing the activity. This is actually really easy to do. It's just an algorithm development thing that requires I guess, a software engineer for lack of better terms, or more time on our side. But yes, we see exactly the same thing in the seismic data.
Well, just thinking about, because you're moving into the sort of gravity driven flows and stuff, is there a way of using this kind of technique submarine landslide flume? Could you instrument submarine
Yes,
systems
we
as well?
use it with other forms. There's additional considerations like, how the sound propagates in like underwater channels, and it depends a lot on the recognition, but it's been done before actually. Not by myself or any of the people who work with me, but some of the other people that have worked on that and for